Hello students. Let's start with the next chapter of our syllabus. Today we are going to start the new chapter that its name is what? Mechanical properties of the fluids. So see here, the word fluids comes here. So substance which can flow, that is said to be fluid. Now we know that solid cannot get flow. Okay. So liquid or gas can flow from the pipe. So that liquid and gas together they are said to be the fluids. So fluids are nothing but the substance which can flow, that is said to be the fluid. But solid can't be flow, so solid does not come in this fluid. Fluid is only either liquid or it is gas or combination of both, because both are flowable, they can flow, that's why they are said to be the fluid. Now here, before going in detail, already we have learned in 11th standard little properties about deformation of solids and so on, elongation of solids. Here the one of the some examples they have given in your book. Let's see what are the example. The examples are air. Air is a gas, water is a liquid, so these are the fluids, example of fluid. Flour, duff means that we will make a chapatis from that can also flow. Toothpaste, the toothpaste we are using to clean our teeth, that can also flow. So that are nothing but examples of the fluid. Apart from this, the lava coming from the earth center, that can also flow, so that is also the example of fluid. Now here, to study the fluid under the action, under the motion, when the fluid is in motion, it is very complicated to study it. So it is better to understand the fluid first in terms of a rest. If the fluid is there and it is at a rest, it is easy to understand and simple way to understand. So that's why we start with that one. So in this chapter, we have to learn the fluid which is at a rest, what type of forces are acting there, that we have to see. So let's start with the example here. They have started with an ideal fluid. Let's start with the first ideal fluid. How the ideal fluid behave, and they have given some properties of ideal fluid. So the first property is incompressible. So the ideal fluid, first of all, let's see ideal fluid. Ideal fluid has some properties. One is said to be, the first property is said to be incompressible. So incompressible. Incompressible means what? The fluid cannot get compressed. The fluid cannot get compressed. We cannot change its density. That is nothing but incompressibility of the fluid. So this is the ideal property, first property of ideal fluid, that is incompressibility. We cannot compress the fluids, and that means what? Density of the fluid is always constant. Second property they have mentioned, irrotational. Fluids are irrotational. Irrotational means what? When the fluids are flowing, there is no rotations. There is no rotations, that is irrotational. Or we can say in your book, the flow is smoothly they are flowing. Smoothly they are flowing. There is no rotational flowing of the fluid. That is nothing but irrotational. There should not be turbulence or disturbance. They are moving smoothly. Okay, so that is nothing but irrotational. Second property of ideal fluid. Third one, it is non-viscous. What exactly non-viscous means? Non-viscous means, it is one of the property. Non-viscous means the viscosity of the liquid or the viscosities of the fluid is zero. So the viscosity is zero, or the fluid doesn't have any viscosity, that is said to be non-viscous. The fluids are non-viscous. And the fourth property, it is steady. The fourth one, it is steady. Steady means what? They are at constant speed. They are moving with a constant velocity or in constant time. So in equal time, they will travel equal distance. So that is said to be, they are nothing but a steady. The flow of the fluid is steady. Constantly they are moving. Smoothly they are moving. So these are the four property of the ideal fluid. Apart from this, so see, fluid means what? We have already seen. The substance which can flow, and the flow can be possible with what? Gases as well as the liquids. So gas and liquid comes under the fluid, but solid cannot come under this. Now in your book they have used some word. That word, its name is what? They have used the word shear modulus. What exactly shear modulus is? They have used in your book shear modulus. If you remember, in 11th standard we have learned this modulus of elasticity. Shear modulus is a property of solids only, because solid has specific shape. We can change the shape of solid, and for that solid opposite, solid resist for its change in shape, and that contains shear modulus. But see, what about liquid and gas? You can pour a liquid in any pot or any vessel, as well as gas also. The gas and liquid acquire the shape of that vessel. So that it means what? The liquids does not resist change in shape, because they just drop in anything, they got the shape of that particular chamber. But in case of solid has a restriction. Solid always resist or oppose the change in shape, and that's why this shear modulus is a property of solids only. In your book they have given some figure 2.1 and 2.1 and 2.2 A and B. What exactly they have mentioned here? Suppose the solid is like this. Solid is fixed between A, B, C, D, such that this surface BC is fixed to the table. It is stick to the table. Now I have applied some force, horizontal forces from this side. I have applied some horizontal forces from this side AB. It is seen that the surface BC is fixed or stick to the table. It can't get moved. Then what get occurred? The shape get changed. So it gets shifted like this. It gets shifted like this. This thing get occurred, and this is nothing but a change in shape of solid. Change in shape of solid. This is the case for solid only. Apart from this, the two more figures they have given 2.2 A and B in your book. The one is compressive. Compressive means what? Suppose we have taken this as a block of the solid. So suppose this is a block of the solid we have taken. In this solid, if we apply the same forces, some forces is applied from all six sides. So these forces we have applied from all six sides. These are the four. Fifth come from top and six come from back. From all six sides, if we apply the force on that particular cube of the solid, then dimension of that cube get decreased, and that is said to be compressibility of solid. Apart from this, same thing we have done. Instead of applying the force toward inside, if we stretch it outside, if all these forces again applied from all six sides, such that we are just stretching the cube like this, and that is said to be the thing tensile. Tensile means we are stretching it, elongation in the solid, and that is possible with the solid only because solid has a specific shape and size, and that this property already we have learned in 11th standard. And due to this, when we compress it or stretch it, what can occur? Deforming forces, internal deforming forces are created whose magnitude is equal to applied force, and that deforming forces move that solid to its original shape again. That already we have learned, so we don't go in detail of that. Let's go next. Here, ideal fluids on the other hand, they are subjected normal compressive stress. Basically, the ideal fluid, when we drop into some chamber, the ideal fluid means gases and liquid doesn't have a shape, doesn't have size. So doesn't have a shape, they can have a size. So when we drop that fluid, maybe liquid or gas, in any shape, they acquire the shape of that chamber or that beaker. So what that means? They does not oppose the change in shape. Does not oppose the change in shape. Ideal fluid does not oppose the change in shape. They acquire the shape of that pot in which we put it. That's nothing but a ideal fluids. So there is one figure 2.3. Here is a vertical plane that they have mentioned, just like a vertical plane like this, and the forces are acting from both sides like this. This is one force and this is another force inside the liquid, inside the fluid we can say. So that thing they have mentioned. Apart from that, they have given some properties of the fluid. So let's start with the properties of the fluid. They do not oppose deformation. Do not oppose deformation means what? Just drop them in any pot, they acquire the shape of that pot. There is no opposition. So they do not oppose deformation. They get permanently deformed. Automatically they get the shape of that particular pot. Second property, they have ability to flow. Liquid and the gases, when we put in the pot, if the pot is tilted like this, we put it here, they have ability to flow. They can flow like this. So third one, they have ability to take a shape of the container, that already I have told you. In which container we put the fluid, they acquire the shape of that container. So these are some of the properties, and these properties we have learned. After that, remember this topic is there. Just this interesting topic. Just try to read it. They have just use the example of brake fluid. Brake fluid. Some brake which work on the fluid, and when that brake work on the fluid, there is no gas. Okay, that is nothing but thing. Apart from this, second parameter they have mentioned this. In medicine, sometimes doctor suggests us that to take a plenty of fluids. Plenty of fluids means take large number of quantity of fluids. Fluids may be the little bit gaseous, it may be the liquid form of water, okay, or water soluble juices. So let's go fluids at rest. The next topic is what? Fluids which are at a rest, and that we have to see the branch of physics in which fluids are at a rest, and that branch of physics is said to be hydrostatics. So let's start with this fluids at rest. Fluids at rest. So fluids are at rest. Already I have told you, when the fluids are moving, it is little bit complicated to study it. So let's start with the fluids at rest, or it is the branch of physics which deals with the study of the fluids which are at rest is said to be hydrostatics. Hydrostatics, the branch of physics which deals with the study of fluids at rest is said to be hydrostatics. Now let's start with some of the properties of this hydrostatics or fluids at rest. The first property is nothing but a pressure. Pressure means what? When the fluid was kept in a container, or beaker, the fluid exerts some force on surface of container, walls of container, as well as the bottom of container, and that forces applied by that fluid on the surface or wall per unit area is said to be the pressure. Suppose the pressure would be represented by P, and the force applied by the fluid on the wall of container is F, and the area on which it will apply the force is suppose A, then the pressure can be given by this formula: P equal to F divided by A, force exerted by fluid on wall of container or base of container having some area A, that force applied per unit area consist of the pressure, that is said to be pressure. We can say pressure exerted by the fluids on the wall of container or surface of the container. Let's go again. In your book there is one figure 2.4. They have just taken one thing, just they have taken a vertical face. Suppose fluid exert force on vertical surface. Suppose this surface, this is fluid applying some force from this side, or we can apply the force from this side, okay, vertical. Same thing, if this is a surface, the horizontal surface, the fluid can apply force like this, up to bottom, or it is bottom to up. Same thing they have mentioned. And here remember, if applied weight is very small, suppose in this beaker, or suppose we have taken a very small area, suppose we have taken this beaker, this is very small area we have taken, and here some of the liquid is kept here above the surface. We have kept some, this much liquid is above this point A. Then this weight of the liquid or fluid above this point is very small. Still, force applied by this on this area A may be large. If the area is very small, small weight of fluid can apply very large force, and that they have mentioned here. For example, they have taken 10 Newton acting on 1 centimeter. The force of, if you apply force of 10 Newton on the surface of 1 centimeter square. When we apply the force 10 Newton on 1 centimeter area, it is seen that the pressure exerted would be 10 raised to power 5 Newton per meter square. Remember, it's very large. 10 raised to power 5 Newton per meter square means it is 1 lakh Newton per meter square. If 10 Newton of force is applied on 1 centimeter square area, the total pressure exerted would be 10 raised to power 5 means 1 lakh Newton per meter square. Instead of this, if you apply 10 Newton of force on area 1 meter square, then what is the force? 10 Newton per meter square. Not a force, it is a pressure. The pressure would be 10 Newton per meter square. Now what is the change here? This area we assume here is large. This area we assume here is small. So when on small area we apply 10 Newton of pressure, 10 Newton of force, the pressure would be 1 lakh times. Same pressure we have, same force we have applied, but area get increased to 1 meter square, the pressure applied is 10 Newton. 10 and it is 1 lakh. That much is the difference. Small weight of the fluid on very small area can increase the pressure. Small weight of the fluid applied on large area decrease the pressure. That point they have mentioned under this topic. Apart from this, they have given the unit of pressure, just pressure. Force can be measured in Newton, Area can be meter square. So Newton per meter square is a unit of this pressure. Apart from this, if you remember, in 11th standard already we have learned about the dimensions. Fourth chapter, fundamental quantities, derived quantities that we have seen. In that case, we have already learned how to find a dimension. So units are Newton per meter square or dyne per centimeter square, and dimensions they have given in a book: L to the power minus 1, M to the power 1, T to the power minus 2. So all of you have the homework. Just try to find out a dimension of pressure, put the dimension of force, divide by dimension of area, find it out, we get dimension of pressure. You can find it out. Apart from this, the different things, the pressure is scalar quantity. It required magnitude only. It does not require a direction. It required a magnitude only, does not require a direction. So it is scalar quantity. Apart from this, they have given a different unit of pressure that are nothing but bar and torr. So this bar is another unit to measure the pressure, or it is said to be another thing is torr. The pressure can be measured either in bar or torr, or in pascals also, or in Newton per meter square also, dyne per centimeter square. These are the unit to measure the pressure of a fluid or pressure exerted by the gas. And here they have given the relation: 1 bar equal to 10 raised to power 5. 1 bar equal to 10 raised to power 5 Newton per meter square. That is the relation between the bar and Newton per meter square. Again, the next, the 1 hectopascal. Pascal is again the unit to measure the pressure, and that was represented by PA. Pascal is a unit to measure the pressure. 1 Newton per meter square. 1 Newton per meter square is equal to 1 Pascal. 1 Newton per meter square is 1 Pascal. Apart from this, they have just given another unit, that is nothing but what? That is nothing but a hectopascal. 1 hectopascal is 100 Pascal. 1 hectopascal is nothing but equal to 100 Pascal. You have to remember this conversion, might be required in numericals. So for that you have to remember. After that, in your book there is a blue color line. It is very interesting and you have to use your own brain. So what is the, just I will tell you the what is meaning of that question. Answer you should find. If you can't find it out, then I will tell you. Okay, but try to find it out first. Use your brain. So that's why they have used the word use your brain power. Okay. So see, the first, can you tell why does a knife has a sharp edge and needle has sharp tip? When we consider knife to cut fruits or vegetable, the knife has at the bottom, it has very sharp edges at the bottom. Why it's so? In case of needle has at the tip, it is sharp edge. Why it's so? Try to find out the answer. If you got the answer of this, you will understand this topic, whatever I had told you here. The next one, use your brain power. If the student of mass 50 kg, if there is one student whose mass is 50 kg, standing on both feet, both two legs standing on the floor, okay, and estimate the pressure exerted by student on the earth. Find out, just estimate, find out approximately how much is the pressure exerted by that student whose weight is 50 kg on the earth's surface when he is standing on two legs. At the same time, if that student is horizontally slip on the earth's surface, find out the pressure and what is the difference, and then just compare when the student lies back, what would be change in the pressure. Take approximate value of acceleration due to gravity, 10 meter per second square. So do it, try to find out. You get a little bit different answer, and that answer is very important. Already if you remember, we have seen here 1 centimeter square is the area, 1 meter square is the area. What is the pressure? 10 raised to power 5. Here what is the pressure? 10 Newton per meter square. That is a change in the pressure because area get changed. When we are standing on the two legs, our area of the surface or earth on which we are standing is very small. When we go to back, sleep on the earth's surface, area of contact with the earth get increased and accordingly pressure get increased. It is very interesting thing. Try to solve it. Try to imagine. Don't solve. Try to think over that topic. The next topic is what? Remember this next page. Again they have given the concept of pressure is useful in dealing with fluids. Concept of pressure, density are useful when we deal with the fluids. Instead of force we have to use the pressure and density instead of force and mass, because it is compatible for fluids. That's why we are not using the force and mass further. We will use the pressure and density of the fluids. It is little bit easy to understand by this method. The next topic is what? Next topic of our syllabus, pressure exerted by the liquid inside the liquid, pressure exerted. So that we have to find out. So let's start with here, pressure due to liquid column. So let's start with pressure due to liquid column. I will write like this, pressure due to liquid column. So let's draw diagram as from your book. So let's suppose this is diagram, just for sake of understanding we will draw it. For sake of understanding we are drawing this diagram. So let us suppose this is diagram according to book, we try to draw it. Then afterward, this is the level of the liquid above the, suppose this is the water we have kept in this, okay, they have shown in blue color in your book, and in this water or in this fluid, we can say, not a water, we don't use the word water, suppose it is a fluid, any type of fluid. In this fluid they have kept one cylinder, they have kept such type of cylindrical shape. Here suppose such cylinder was kept in this fluid whose area at the bottom is A and its height is suppose H. A is the area, height is H. That cylinder was kept in a fluid in a beaker. In the beaker fluid we have taken, and in that we have poured or put the cylinder whose height is H and area of the bottom is A. Now under this condition, as we know, whatever the fluid inside this cylinder, it has some mass, so it will exert some force, downward force due to gravity. Mg will act on it. So some force due to gravity act on this. So we can find out here pressure, as we have learned. Pressure equal to force divided by area. Okay, force divided by area. What is the force exerted in downward direction? It is mg. Mg divided by area of cylinder. Okay, so I will write it here again A. Just suppose it is A now. Then we will further solve it further. Okay, so suppose it is A. Now we know what is the mass. So density, suppose density will be represented by rho. In your book they have used rho. Rho equal to what? Density, it is mass per unit volume. Okay, from this find out the value of mass. Mass equal to rho into volume. Rho into volume. Okay, that simple equation we have to find out. Density is mass divided by volume. Mass equal to density into volume. That we have to find out the formula. So what is the volume of cylinder? This cylinder has volume, area into height. So we can write this mass equal to the volume into rho, or rho into volume. So rho, volume means what? Area A into height H. Area A into height H. So what we get? Rho dH, or we can say rho dH we get here as nothing but what? Something is wrong, na? dH. D, how can we take D? It is area into height, na? You should take A. Area into height is a volume. So rho as it is, volume is A into H. So same thing can be written as A H into rho. That is a mass of the fluid in the cylinder we have find out. Okay, now just put this value of mass in this equation. Put this value of mass here in this equation and rewrite the P. So we can write here P equal to M is what? A H rho divided by A and this G as it is into this G. So A get cancelled out. So pressure would be H into rho into G, and that is very important to us. And this is nothing but what? Pressure due to liquid column. Liquid column can exert this much pressure, P equal to H rho G. Now remember, pressure exerted by liquid column does not depend on area of this cylinder. Does not depend on area, does not depend on anything. It depends on what? Height. It depends on height, density of the fluid, and acceleration due to gravity only. That is the point to remember. So see this next topic in the same thing. They have just again the blue color shape, purple shape. Remember this. P equal to H rho G. Pressure exerted by fluid at rest is independent of shape and size. Independent of shape and size of container, and as well as it is true liquid as well as for gases. This equation is true for liquid or gases, or in general fluid. Fluids may be the liquid or gas. So this equation for pressure exerted by the liquid column, pressure exerted by the liquid column, or pressure due to liquid column, this equation is applicable for gases as well as liquid. You have to remember this equation. Now let's go further. The next topic of our syllabus is what? Atmospheric pressure. What is meant by atmospheric pressure? Might be all of you are well known about, or all of you have heard this word, atmospheric pressure. Let's see what is atmospheric pressure now. So atmospheric pressure is nothing but a pressure exerted by the air. So we know in the earth atmosphere, earth is surrounded by mixing of different gases. That is said to be air. Air is a mixing of different gases. Air has some weight. So that air exerts some pressure, force, not a pressure. Initially it will exert some force. So air exerts some force on each and every part of the earth's surface. And that force per unit area is nothing but a pressure, and that was exerted by atmospheric air of earth. That's why it is said to be atmospheric pressure. Atmospheric pressure is nothing but what? Pressure exerted, force per unit area exerted by atmospheric air. That is said to be atmospheric pressure. Roughly we can say it like this. Now here, so how to find out the atmospheric pressure? That is very important. So see, as we are on the earth's surface, atmospheric pressure is maximum on the earth's surface. Suppose we have drawn here, this is at earth's surface. On this earth's surface here, atmospheric pressure is maximum. As we go above the earth's surface, it is seen that atmospheric pressure decreases. And if you go further away, it again decreases. And at certain distance above, suppose we go above 8 km, it is 8 km up to this. If you go above 8 km from the earth's surface, atmospheric pressure is negligible. Same thing can occur with the density of air. Density of air is maximum on the earth's surface. As height above the earth's surface increases, density decreases. And at above 8 km, density is negligible. We can neglect it. Very small value of density we get above 8 km. So what we can say, whenever we find out atmospheric pressure, you should take the air column within this area. Suppose this is atmosphere or Earth surface above this 8 km. Whatever be the air particles are there, they will contribute, they will exert some force. This air particle up to 8 km, they will exert a force on the area on the earth's surface, and that force divided by area, it will give the atmospheric pressure. Atmospheric pressure is maximum on the earth's surface, and as we goes up, the air becomes, quantity of air get decreases, and that's why mass of air get decreases, and that's why the pressure get decreases. That is very simple thing. So the atmospheric pressure maximum at earth's surface, or they have used another word, atmospheric pressure at sea level. Earth's surface sometimes is said to be sea level is maximum. At height of sea level, atmospheric pressure is maximum. Above that, up to 8 km, whatever be the air that exert a force on that object having some area, that force per unit area is nothing but a atmospheric pressure. And this is nothing but what we have seen, atmospheric pressure. How to measure atmospheric pressure? Apart from this, they have used one word, vacuum. What is meant by vacuum? If some container would be there within on the earth's surface somewhere here, this is container, such that inside this the pressure is less than atmospheric pressure. Inside this container, pressure is less than atmospheric pressure, then this is said to be, roughly, it is said to be vacuum. Roughly, remember, roughly it is said to be vacuum. Basically, vacuum is what? Vacuum means what? Vacuum means there should not be any atom or molecule. That is said to be perfect vacuum. Roughly, if the pressure inside any container is less than the atmospheric pressure, we can say vacuum get created. Ideally, nothing should be there. There should not be any particle, there should not be any atom, molecule, then it is said to be ideal vacuum. Same thing they have mentioned in the second paragraph, that when gas pressure is considerably smaller than the atmospheric pressure, we can say the vacuum get created. Now let's go absolute pressure and gauge pressure. The next topic of the same, absolute pressure and gauge pressure. What is meant by absolute pressure? When it get created, that we have to see. Let's start with absolute pressure and gauge pressure. Gauge pressure. So we have to learn these two parameters, and we have to see what is meant by absolute pressure and what is meant by gauge pressure. So let's start with this. To to understand this absolute pressure and gauge pressure. So in your book, let us consider the cylinder. Again, just we have to draw one diagram here. So I will draw here the same diagram, that little bit modification. We will draw it. So this is the cylinder which contains some water or some fluid we have taken in this. And again we have to consider here one cylinder. Inside this we have kept some cylinder like this. Okay. In this cylinder, again they have taken some parameter. The force act on this at the top is F1. Due to the fluid above the cylinder, it will exert a downward force F. And within the cylinder, there is some fluid whose mass is mg. It acts in downward direction. At the same time, below the cylinder here at the bottom, there is some fluid. So it will exert opposite force, and that is nothing but a F2. Opposite force, that is nothing but a F2. X1 is a highest point. This is X1. Let us consider this is X2. X1 is greater than X2. Same thing, pressure at X1 is P1. And here the pressure is suppose P2. So these are the assumptions we have drawn here. So what is this? Above this cylinder, some liquid is there. It will exert downward force, that is F1. Within this cylinder, there is some fluid, has some mass. So it will exert a downward force due to acceleration due to gravity, that is mg. And below this cylinder, again there is some fluid. It will exert opposite force on the same cylinder, that is F2. Let us consider the length, that height of this cylinder can be found out by these two parameters, x1 highest value, x2 lowest value. X1 minus x2 give the height of cylinder. And this P1 is the pressure at this x1 place, and P2 is pressure at the bottom. X1 is the pressure, P1 is the pressure at top. So these are the assumptions. Now let's find out the forces acting. Already we have learned F1 mg acting in downward direction, F2 acting upward direction. So we can write here one simple equation. One simple equation we can write. This F2 equal to upward force equal to downward force, F1 plus mg. So we get this equation 1, suppose. F2 equal to F1 plus mg is equation 1. Now we know, as we have just derived one equation, we have written pressure equal to force divided by area. So this implies that force equal to cross multiplication, pressure into area. So this formula we can write here, and accordingly we can write here one simple thing, pressure into area. So see, we can write for first it is F1 P1. For first force F1, the pressure is P1, area is A. Similarly for second, you can write F2 equal to P2A. I will write it here. F1 equal to P1A and F2 equal to P2A. Suppose this is equation 2. Just I have written here to understand it well. I have written it properly. Now we will erase this part. So this is nothing but what? Equation 2 they have taken in our book. Now let's go further. The mass we have find out. So again, density rho equal to mass per unit volume is density. So this implies that mass equal to density into volume. Density into volume, that already we have learned. Density into volume, so that already we have learned initially. So same thing, what is the density? It is rho, so we can write rho. Put the volume of solid cylinder in this solid cylinder or hollow cylinder, its volume. So we can write this rho into volume means what? Area into height. Okay, so what is the density as it is? Area of cylinder is what? That area of cylinder, suppose it is A. Area of cylinder A, height we can find out x1 minus x2. So you can write x1 minus x2, that is nothing but a mass. That is nothing but a mass of the fluid in the cylinder. So I will write it here again. M equal to rho into A into x1 minus x2, it will give the mass. Suppose that is equation 3. Suppose that is equation 3. So we have written these 3 equations. Now let's go further. So I will again erase this part. So this part already we have learned in last topic also. So same thing, we have written 3 equations. First equation, upward force equal to downward force. Second equation by the pressure, and third equation by the density. We have find out the mass. So these 3 equations we have written. Now just put these values. Put this value of F1, F2, M in this equation 1. Put equation 2 and 3 in equation 1. What we get, I will write here. F2 means what? P2A, so we'll write here P2A equal to F1 is what? P1A. So it is P1A plus M is what? Rho into A into x1 minus x2, that is mass, into acceleration due to gravity g. Now let's look at this equation. Here A is common. So take it common or divide both sides of the equation by A. So this A get cancelled out. This A get cancelled out. So what equation we get? P2 equal to P1 plus rho x1 minus x2 into g. This is the equation we get. So same equation they have taken as a 2.6 in your book. So P2 equal to P1 plus rho x1 minus x2 into g. They have taken g initial, doesn't matter. The concept is remains same, so that we can get this equation. Suppose this equation 4. Suppose this equation 4, and this equation gives us a pressure exerted. Pressure exerted. So there, just see what they have done. This equation can use to find out pressure inside the liquid. Just they have mentioned inside the liquid below the level of the beaker, we can find out the pressure bias in this equation. Same thing, suppose we are going to find out atmospheric pressure. Okay, to find out atmospheric pressure at certain height, you can just put some values in this and just we go to the next diagram. Suppose this cylinder is inside the fluid we have taken. Suppose this cylinder we have adjusted such that this x1 part come to the surface. I have just made a modification in the same diagram. Suppose we have adjusted like this. Cylinder is kept such that this x1 come to the surface, x2 come inside the liquid or in the depth at height of minus h, we can say. This would be the height of minus h inside the liquid. The top surface come at the surface. Now here put some values and just put it here. Same equation we can write. If we put in this equation by this diagram, that was a diagram in your book as a 2.8. Put here x1 equal to 0. At the top we comes now. So let us assume it is 0. Okay. And here put P1 equal to P0. P1 equal to P0, comma P2 equal to P. Why is P0? P0 is atmospheric pressure. It comes in atmosphere, so it is atmospheric pressure. P is the pressure inside the fluid. Okay. P2 equal to P. X2 equal to minus H. In this equation, if you put, we get atmospheric pressure. So we can write here P2 equal to P. We should put P equal to P1 equal to P0. P0 plus rho as it is, x1 as 0 minus x2 as a minus h, minus of minus h, it is nothing but directly I will write it is rho into h into g. So we get this equation P equal to P0 plus rho h g, that is equation 2.7 in your book. By this equation you can find out the value of this pressure P. Now here they have used the word absolute pressure. This equation, the total pressure or absolute pressure P at a depth h below the surface of the liquid. This equation gives the total pressure P at this point P2 at a depth of minus h inside the liquid. This pressure can be found out with equation atmospheric pressure plus rho h g. That this equation already we have derived rho h g. So this P0 get added because atmospheric pressure comes here. That's why we can write it as P equal to P0 plus rho h g, and this is said to be absolute pressure. This equation is said to be absolute pressure. This is the equation to find out absolute pressure at a depth h inside the fluid that was given by this absolute pressure. And this is nothing but a equation for absolute pressure. Let's go further. Again in your book they have another diagram. They have find out. Before going into that diagram, let's see first one equation modification. In general, the difference in atmospheric pressure and pressure inside the liquid, that will give the gauge pressure. Gauge pressure is defined as the difference in the atmospheric pressure and this nothing but what? Inside the pressure inside the liquid or fluid and atmospheric pressure, the difference gives the pressure that is said to be gauge pressure. So let's see on page number 30, left hand side at the top. In general, difference between absolute pressure and atmospheric pressure is called as a gauge pressure. Same thing they have mentioned. So do it here. P, just I will write it here. I will write here P minus P0. Move this P0 to this side. P minus P0 equal to rho Hg. And this equation gives what? Gauge pressure. It is said to be gauge pressure. And our topic is this. We have seen absolute pressure is this. Absolute pressure inside the liquid at a height minus h below the liquid is given by this equation, that is said to be absolute pressure. And absolute pressure minus atmospheric pressure gives the gauge pressure. Same thing they have done. Apart from this, we can just again modify this diagram. We can modify this diagram, move the cylinder above the normal level, and we can draw it. And same thing they have done in figure 2.9. I will draw the same figure again here, little bit modification according to the book. So see, this is the normal level of the fluid, and we have kept here cylinder such that the cylinder comes like this. It goes up. Cylinder goes up now. And again the parameter remains same. So here it is P1 equal to P, suppose. P1 equal to P, suppose. It is x1 here. Here it is x2 at the bottom. And at this P1 equal to here P2 equal to P0. P2 equal to P0 atmospheric pressure, and this is a distance d above the fluid level, at a height or distance d. Now if we put these values again in the equation, in the same equation we can put, or this equation we can put, instead of this put it here, in this equation put these values, what we get, the new equation we get, I will write the below this equation, I will write the same new equation. So P equal to, after putting that value, what we get, P equal to P0 minus D height h, here it is D rho, and it is G, D rho G, and rho here and G, but here it comes to be P0 pressure of air. So this density of, not a fluid, it is density of air. See, this is density of fluid. Rho air means density of air, that we have to consider now. And this equation gives the absolute pressure at a height d above the fluid level, and that was given by P equal to P0 minus D rho air into G. Why the minus sign come? Why it is plus sign? Because here H we have taken minus H. Here it is plus H because it is plus D. It is going up. It is plus D. That's why it come to be plus minus become minus. It is D rho air into G. That is nothing but this pressure. Now let's go to next part of the syllabus. And this is nothing but what? Simply again below this topic they have just given you the simple can you tell point is there in blue color. In that case they have taken three different figures, three different shapes they have taken, and their height is same. Three different shape, height is same, and they want to ask you the simple question. In this three container filled with the same oils, the oil is same, fluid is same, how will the pressure at the reference lines compare? Pressure at reference line is maximum in which pot, that we have to find out. Try to find the answer. If you don't get, then we will discuss later. Now let's go next topic, hydrostatic paradox. Hydrostatic paradox. Hydrostatic paradox is one of the paradox. Initially, either scientists are not well known about this theory. So there is one paradox. What is that paradox that we have to see? So see, in your book they have just given figure 2.10a. So just I will try to show you 2.10a here, but it's quite difficult to show you. So just I will draw the figure. Try to draw rough figure. So let's draw it here. Suppose I will draw it like this. So the first cylinder is here, they have taken, okay. Then what they have done, they have taken just such type of another thing. They have taken second part like this, okay. Height should be same. So then, so I will make it height like this. So it will height. Then third parameter they have taken here like this. Here the small opening would be there, and this for this they have shown like this. Such type of thing they have taken. Just such type of bigger part they have taken. So this is the third, and fourth one they have taken, and that is nothing but what? Just a little bit different way. It is like this, okay. So let's start with this. This would be like this, and here there is a little bit square part like this, and it goes up like this. such type of 4 different shapes they have taken, and they have given the names as A, this is B, and this is C, and this is nothing but a D. And this all is filled with liquid. Suppose this liquid get filled on this, all this, the filled with the liquid. Suppose these are the liquid, they are filled with this. Now you can observe that in this container they have different shapes A, B, C and D. While when we pour liquid from any shape, either you pour liquid from A or B or C or D, you can see that as we pour the liquid, the level, horizontal level of all is same. Horizontal level like this, it must be same. It must be same. And if you drop a liquid in this particular vessel from any part, it is seen that the liquid rises at same horizontal height. Now the question comes, how it's possible? Initially scientists say that if you see the figure C here, this shape, here it is conical part. So liquid exert more pressure at this point C. It is observed that liquid exert more pressure at point C, and at B, the pressure exerted at this part is less. Here the pressure exerted by this liquid is maximum, here it is minimum. That was thought of the scientists at that time, and it will create a paradox. Paradox means the error, and they say that pressure at point C due to vessel C must be maximum, and due to that when we pour a liquid, this pressure rise the liquid in vessel B also, A also and D also at the same height, because this pressure is more, so they come to same height. That was the assumptions initially by the scientists, but that was the wrong, because already we have derived the equation for pressure. Pressure, it depends on rho H into G. Pressure of exerted depends on rho H G. It does not depend on area. It does not depend on any shape. It depends on only height. If height of all of them is same, see this height is same. Height is same, so there is no change in the pressure, and that's why this paradox arises, and that is said to be hydrostatic paradox. Same thing they have mentioned here. Apart from this figure A in your book, same figure B they have mentioned here. But I will draw here figure B like this, so it is figure B. So they have drawn this as a figure B, and in this figure B, what the modification they have done? Just they have applied some forces like this. Some forces are applied parallel to edges. These are the forces applied parallel to edges like this. These are the forces. So not parallel, applied perpendicular to edges of this shape. Perpendicular to this tilted part of this vessel. They have applied these forces. Now here they have divided this face or this vessel into 3 parts. Suppose we have taken this as A, again this as a B, and this as A, this is A, and this is B. So these forces applied on this surface and this surface, they can be split into vertical component as well as horizontal component to balance the forces or weight, to balance the weight. But what about this central part B? In this central part B, that will exert a force due to gravity mg in downward direction only. It will exert a force due to gravity in downward direction. So this is not a longer paradox. This paradox cannot arise here. So whatever be these forces we are applying perpendicular to these edges, that can be split into vertical component and horizontal component. But about this central part B, the whole weight cannot be balanced. Upward force is not balanced here, and that's why it goes, resultant force goes in downward direction. The same thing they have mentioned here. Now next topic is a Pascal's law. So already the video is very much long. So first of all, just whatever I have taught you today, it is a basic conceptual part. Nothing to worry about. This is a very simple part we have seen up till now, introductory part. So you just revise this part, and next video we will start the Pascal's law. So just watch my video. While watching, put a book in front of you and first watch it, and then read the same topic from your book for your better understanding. Thank you.